Okay, so this is the acetylcholine receptor. And again, this is an archetype for the ligand-gated ion channels. That's being acetylcholine right there. The neurotransmitters are going to be small, diffusible molecule that will communicate nerve impulses, synapses. Some of the examples would be the acetylcholine, which is probably one of the more famous examples. This stimulates skeletal muscle contraction. And so you've all probably heard of acetylcholine at some degree, somewhere, I hope. The synaptic cleft, this is going to be approximately a 50 nanometer gap that's going to separate the presynaptic membrane of the synapse and the postsynaptic membrane. You know the pre versus post, right? Pre is where the signal will come from. Post is where you'll get the signal propagating to. Synaptic cleft is that space in between. Okay, so this right here is the diagram of this. So again, that synapse is going to be the gap between the cells where the nerve impulses are transmitted. There we go. Arrival of a nerve impulse at the end of the axon causes the synchronous export of the contents of your vesicles of your neurotransmitter into the cleft, which again, here's your cleft. The neurotransmitter binding to the postsynaptic membrane is going to trigger that action potential. So whatever the result of that signal would be, whether that's propagation to another time or whether that would be release of some chemical. Okay. Again, here's our direction of nerve impulse. You can always tell this because pre happens before post, right? So pre and post. Again, this is the presynaptic membrane. This is your axon here. The synaptic vesicles are right here. They're going to empty out into the synaptic cleft here. That's going to cause that binding to the postsynaptic membrane, which will then cause whatever your action potential will be. Okay. The acetylcholine receptor is going to be the best understood ligand-gated channel. It's one of the most widely researched one because it has a physical action that accompanies it, which is really nice. The ligand-gated channel is going to be a channel that's gated not by voltage, but by the presence of a specific ligands. The example obviously being the acetylcholine receptor. This is a non-specific cation channel. What does non-specific cation channel mean? It has low specificity, right? Exactly. We could take different cations in, assuming they have the correct-ish size, okay? And they're cations, of course. Okay, so this is the marbled electric ray. Another name for it is the torpedo. Man, I always have trouble with this. Marmorata. I am not a good atta sayer. It's not a common thing in English. The electric organs, these are called the electroplexus, voltage generating cells. These are going to be rich in acetylcholine receptors. Remember, every time we do this, there is a paradigm we're working on. So we're looking at an archetype by looking at a specific example of it. Okay? Now, the structure of your acetylcholine receptor is going to be the acetylcholine receptor will be a pentamer. This will be 4 kinds of membrane-spanning subunits. We have the alpha-2, the beta, the gamma, and the delta. Okay. How many are there again? Pentamer means? Okay. Pentagon means? 5. And there's how many different types of them? 4. And so notice we have 1, 2, 3, 4 types. How many alphas? 2. Yeah. And that gives us 5. This is going to have approximate 5-fold symmetry. The genes for the alpha, beta, gamma, and delta subunits are going to arise by duplication and divergence of common ancestral gene. Each subunit is going to have a large extracellular domain, 4 predominantly hydrophobic segments that span the bilayer membrane at the carboxyl end. this is what this looks like. Over here's where your key is, by the way. So this is looking down it. This is the easiest place to see all of your 5, okay? And so here we have our alphas. See the 2 alphas here? I have to admit, I very much do not like how they do that sometimes, where they put alpha 2. This would actually be better served by being 2 alpha, right? Because they're kind of not linked. See that? Which causes some issues sometimes. Anyways, so here we see our alphas. Right here is our gamma, beta, delta. Everybody okay with that? Okay. Now, what do we notice about our alphas? Why are those getting conserved? Where's our acetylcholine binding sites? Yeah, we have them right off those alphas, right? Yeah, they'll bind a little bit to the delta here on this end, and a little bit to the gamma here on this end, which have slightly different structures around those acetylcholines. But the majority of the binding site here is actually having to do with the alpha. And you have how many acetylcholine binding sites? 2. So you have how many alphas? 2. Yeah, got it. Okay, so this is to the side. This actually shows you that I think this does a better job of showing you what this looks like. But notice the channel is right there. That would be your pore, right? Wow, I actually got pretty good attendance today. Just took a bit to get. That's okay. That's okay. Oh shit. As long as you're okay. It is fine. I'm not pissed off. Everybody's we're good. Okay, so this right here is again the alpha, but you notice all of them look pretty similar. Okay? Because they're just slightly evolved differences, right? They were copies originally, and then they had changes over time. So right here's your alpha. This is going to be your extracellular domain here. This is your membrane spanning segment there, and this is the segment that's inside the cell right here. And you can see that it has this open part right here, then channels down, and then this is our channel here, right? Okay. Can everybody see the similarities to our previous ones we talked about? It has these 2 parts that can move like that. Okay. And it has your little gap here, and then it has something that can bind to the outside. Yeah, it looks quite similar, doesn't it? Okay, does anybody have any questions about that right now? Again, the acetylcholine binds at the alpha, gamma, alpha, delta interfaces. Okay. So your acetylcholine is going to bind at your extracellular domains. That's this part right up here. This is going to lead to straightening of the alpha helices from the alpha. And in this case, we're just talking about this side, which is the alpha delta. Okay. So this would be your alpha delta. See that? Okay, so right here we can actually see this alpha subunit more closely. And what we're seeing here is that these are the 2 different arrangements, where we have the closed form here and the open form here for that alpha subunit. And that's literally going to be because the acetylcholine is binding, changing it between your open and closed. So again, this is going to be where the ligand binds to the extracellular domain. And that's going to give you the what form? Open. Very good. Yep. Very good. And then not binding, that gives you the closed. Yeah. Well, it was closed before bound. So your equilibrium potential, that's your membrane potential at equilibrium. This is going to represent the balance between chemical and electrical gradients. Remember, these are 2 different separate forms. Chemical gradient would be the concentration gradient, right? The electrical gradient would be your charge gradient. It could be multiple different positive and negative species causing this. Okay. In fact, there are many positive and negative species causing this. The equilibrium is going to be established when your driving force, due to the concentration gradient, is balanced by the electrostatic force resisting your motion of additional charge. And this is why when we're talking about these sodium, potassium, calcium channels, they're all getting mixed together. Is that starting to make sense? Because their potential across this membrane is going to involve all of those, right? It's going to involve how much positive and negative you charge have versus the concentration difference across the membrane. Okay? This is why this all ends up in the same chapter. This is why they all end up one after another like this. And you kind of have to understand them. And then we get to this. Okay? All right, now this right here is your electrical gradient. And we have here a concentration gradient. So the electrical gradient in this case is 0. The concentration gradient is the one we're having to, that we have pushing across. And so what's going to start happening right now at this point here? Okay, we're going to have some different channels open. They're going to be specific channels that are going to allow these positives through, right? Okay. And because our concentration gradient is the only thing pushing, what's going to happen? Positives are going to start flowing through, right? Okay. And so our positives flow through. Now, what's going to happen as our positives flow through? What's happening to our charge over here on the other side? Yeah, we're building up positive charge, right? And on the other side, we're building up negative charge, aren't we? And so what's going to happen is these positives are going to be repelled on this right side, and they're going to be attracted over to the left side, aren't they? And so that means that our concentration gradient now fights against our electrical gradient. Once those forces are equal, it will no longer have any overall flow. Okay? Will we have individual exchanges? Yes. We can have individual exchanges. But again, that will create an equilibrium, won't it? Okay, so this right here is your Nernst equation. You may recognize this from Gen Chem. Remember your Gen Chem 2? Electrostatic stuff? Okay. Just towards the end. This equilibrium potential is going to be described again by your Nernst equation. This is the Nernst equation right here. This is the voltage equal to the negative RT, our gas law constant right here. Notice this will be the one that's in kilojoules. This technically should be Kelvin here, not degree. In this version, it would not be degrees. It would be an absolute temperature scale you'd have to use. This will be then temperature in Kelvin. F is going to be the Faraday constant here. Z is the charge on the ion. So if you're a positive 1 charge, Z is positive 1, right? If you're a 2 plus charge, Z is going to be 2, right? Okay. Okay, and this right here is then the difference in concentrations. Now, this Nernst equation doesn't look like the normal Nernst equation. Okay? And that's because we have little tiny changes in it that are being made because we're in and out of the membrane. Okay? And so this is the natural log, and this is in the membrane concentration of whatever species we're looking at, divided by outside. Okay? Okay. You can use this for any potential difference across anything. Okay? You could do a membrane, you could do a salt bridge, you could do a battery, you could do anything, okay? And this term just is the difference in concentrations across some sort of barrier that's not allowing free flow, okay? Okay. What happens if you allow free flow, by the way? Diffusion, right? And they equal out pretty quickly, okay? Okay, so let's talk about generation of an action potential. So step 1, acetylcholine is going to be released into the synaptic cleft from a presynaptic membrane. Step 2, acetylcholine will bind to the acetylcholine receptor on the postsynaptic membrane. Step 3, the acetylcholine receptor, it will open. Step 4, our potassium ions are going to flow out of the cell and sodium ions will flow in. Step 5, as the membrane potential approaches negative 40 millivolts, the voltage sensing paddles of the sodium membrane are going to be pulled into the membrane and the channels will open. Step 6, the sodium ions are going to flow rapidly into the cell. This is going to increase the membrane potential towards the sodium equilibrium potential. Step 7, your voltage sensing paddles of your potassium channels are pulled into the membrane. The channels are going to be open. It's going to inactivate fairly quickly using the ball domain plug, which will plug the open sodium channels. I guess my sentence structure wasn't all that great there. And the acetylcholine receptors are going to inactivate. And so we're closing off that sodium portion. We're closing off the acetylcholine portion. Okay? Step 8, the potassium ions are going to flow rapidly out of the cell, decreasing the membrane potential towards the potassium equilibrium potential. Step 9 is the inactivation ball domain is going to plug your open potassium channels. Remember, this is how those cut off fairly quickly. Okay? Step 10, once your membrane potential has returned to close to its initial value, your inactivation domains will be released and your channels are going to undergo the recovery. That's that thing where we looked at where it goes around in inversion, remember? Okay. So let's talk about the refractory period. I'm not going to mention how people usually know this term because I feel like that might be sexual harassment. But refractory period is the time preceding recovery in which the sodium channels cannot be reopened by membrane depolarization. A new action potential that cannot be induced during this period. This typically lasts approximately 1 millisecond in neurons. This ensures that the action potential travels along the membrane in one direction. You know what would happen if you had it didn't have a refractory period for your neurons? Okay, so when you have a polarization potential, does it just do it in one direction? No, it doesn't in both directions, doesn't it? Yeah, it would be a little bit more concentrated towards one side of the neuron than other because they're a little bit long, but you would still have that effect on the other side as well, okay? And it could drift around a bit. So if you didn't have any refractory period, you'd actually fire off both directions every time. Okay? Yeah. So the membrane potential is going to move towards the sodium equilibrium potential, then towards the potassium equilibrium potential. And these are the ones what we're talking about. So this is the sodium equilibrium potential up here. It's a little bit above 60. So that's why we were always going up to the positive 60. Remember that? And then we're going to move back down towards the equilibrium potential for potassium, which is the nearly negative 100. Okay? Now notice we don't ever get to either. We're just going to bounce back and forth between. Okay? Okay, so again, we're going to have the negative 60. This is usually where we end up starting. We could theoretically start at something a little bit lower though. Okay? But we're going to be drifting back to negative 60 all the time and dipping below to reset. And so we're negative 60, we go up to about positive 40, and then that's going to cause us to go backwards to the potassium equilibrium. Okay? So bounce towards sodium, go back to potassium. All right? And then we'll drift back up to the negative 60 slowly, and we're completely reset by this point. Okay, so this right here is the current flows through your potassium and sodium channels that underlie this action potential. So this would actually be the time-resolved current flows here. We have the sodium potential, and that's why we're going towards the sodium potential, right? And this is then followed by the potassium potential. And this pulls us back to the potassium potential right there. Everybody see that okay? Now, what would happen if we don't have these two channels working in tandem to do this? Anybody have any idea? It wouldn't be that drastic. It wouldn't be that bad. But what would happen is you'd basically get, see how this drifts like that? It's very slow? That's what you'd get. So it would, if we just had sodium and not potassium, it would come up here in sodium, and then it would slowly drift back down. And we would not get a sharp signal, okay? And so we would keep firing for an extended period of time, and we could actually fire backwards because of it. Yeah. So by working in tandem, we pull it up really fast, and then we have the sodium pulling it down. So sodium pulls up, potassium pulls down. And it's kind of like how, anybody play sports where you swing a bat or something? Where you swing like a bat, a golf club, anything like that? Okay. Okay, so, and you do that with a ball too, it's just harder to talk about. So when you do something like swinging a bat or a club or, you know, tennis, whatever, okay? What you do is you have a pivot point and then a pivoter, right? And the reason you have two of them is you can get a sharper motion, right? By reversing the two. And that's what you're doing here. You're creating a very sharp motion, okay? The sodium bringing up, potassium bringing it back down really fast, right? And this gets you in a normal system, well, in an electrical system, we have something very similar to that, by the way. And that's how we get the very sharp pulses that can do things like give us a Wi-Fi signal, okay? And so we can communicate much faster. What would happen if it took us like a full 100 milliseconds to reset every time? How fast would we be thinking? How fast would Dr. Clausen lecture? Yeah, like one of those sloths, right? Okay, so the state of the sodium-potassium channels during the action potential, this is them being demonstrated. Here's our sodium channel. So it was closed, the potassium channel is closed, our sodium channel opens, and then our potassium channel opens just a little after that. See that? And this right here is your time in milliseconds. And that's what's giving you your very sharp shift, right? Opens, goes up to the sodium. Potassium opens, goes down towards the potassium. Okay? And then this inactivates for the sodium channel because you don't want to keep pumping sodium, right? Because you're going in the reverse direction now. And then the potassium channel will inactivate right here. And then over here, you'd be resetting these, right? Because you finished your signal propagation. Okay. This will drift back up to the 60, which is part of usually that resetting process. So your disruption of your ion channels by mutation or chemicals can be potentially life-threatening, of course. Long QT syndrome, typically abbreviated LQTS, is a genetic disorder. By the way, they do this a lot in the medical field, and it's really one of those points where biochemists and chemists really get kind of weirded out by it. Like CAT scan. Do you know what the T in CAT is? Tomography. Tomography being a type of scan. Or PIN number. The N being number. So PIN number being personal identification number. And they do that all the time. Like you'll hear people go LQTS disorder, LQTS syndrome. Syndrome's already there, guys. Anyways, don't mention it because you'll just be weirded out. And they'll be like, you're a biochemist type. You'll be persecuted. No, you won't. Genetic disorder in which the recovery of your action potential is actually delayed. So this leads to brief losses of consciousness, heart arrhythmia, and sudden death. The QT here actually refers to a particular feature of the cardiac electrical activity pattern. So the most common mutations in LQTS patients will inactivate potassium channels or prevent the proper trafficking of channels to the plasma membrane. And there you go. That's the long-term overall bulk effect if you have a bunch of your errors, okay? Not just the single cell. So, hyperpolarization activated ion channels are going to enable the pacemaker activity in your heart. The heart is going to use a coordinated change in your membrane potential. This will facilitate the muscular contractions that are needed to pump the blood. Your pacemaker is a collection of cardiac cells that initiate an action potential without a neurotransmitter. The most important pacemakers are in the sinoatrial SA node. Your pacemaker cells are going to possess a capacity for mixed sodium-potassium conductance when their membranes are hyperpolarized. This is actually going to be referred to as funny current. Beautiful name, right? Which is I, which is current, by the way, sub F for funny. The current is going to is active at rest and shut off during action potential. Hyperpolarization activated cyclic nucleotide gated channels, abbreviated HCN channels. By the way, the channel is not part of that. These are channels that are opened by hyperpolarization and closed when the membrane is depolarized. The HCN4 isomer is the prominently expressed in the SA node. And so this is the specific channel that we're talking about in the sinoatrial, which is the most important pacemaker of the heart. Okay? And that's what keeps pacing for your heart. Okay, so let's go ahead and, you knew this was coming, right? Every time I bring up a channel or anything that works, to prove that it works and demonstrate it, what do? Find something it doesn't work. Okay? There's a pattern. So your disease-causing HCN4 mutant is going to require greater membrane hyperpolarization to open the channel. So in patients carrying this mutation, you'll have fewer HCN4 channels that are open at a given resting potential. This is going to lead to slower depolarization and reduce your heart rate. An interesting side note to this is, do you know what they found out about Navy SEALs? People that pass the Navy SEAL exams? The people that pass are way more common to have slow resting heart rates that don't vary much. And they also tend to die, even without accounting for the violence of the Navy SEALs. They tend to die about 20 to 30 years earlier. Yeah. So, weird, huh? Yeah. Okay, so here's your percentage of activated HCN4 channels. Right here we have the mutant, and here we have the wild type. Wild type being the quote-unquote normal, right? Okay. And so right here we can see is we have these, they're both 100% at this millivolts. And the mutant is going to go ahead and have a higher percentage right here. That'll be the activated, deactivated channels. See that? Yeah. And so you have a faster curve of deactivating these channels or having inactive channels than the wild type. Wild type would have more active channels at a given millivolts. Okay. It's not a huge difference though, right? Which is why we can actually look at these and be alive. All right, so let's talk about gap junctions. These are going to allow ions and small molecules to flow between communicating channels. Your gap junctions are going to be gap junctions. The other name for these are cell-to-cell channels. I have almost never heard these called cell-to-cell channels, by the way. Gap junction is wildly more popular there. The channels that serve as passageways between the interiors of contiguous cells. These are going to be clustered in discrete regions of your plasma membranes. They're going to allow for polar molecules with a mass of less than 1 kilodalton. They're important for the intracellular communication and nourishment of cells that are distinct from your blood vessels. They're going to form readily when cells are brought together. They're closed by high calcium, 2+, and low pH. So the gap junctions are going to form tightly packed arrays. We can actually sort of see this here. So we have tightly packed in a regular hexagonal array. And each gap junction is going to have approximately a 20 angstrom central hole. And so it is large enough that you can view it. And we're seeing that right here. Can you see the little hexagon shapes? They actually show quite nicely, right? It's a real world thing, so they're not perfect hexagons every time, but you can very clearly see the pattern, right? Okay. Because what did we learn about real world? It's damn messy in it. Okay. Okay, so the connexin and connexons, connexin is going to be the transmembrane protein containing 4 membrane-spanning helices. Connexon are also referred to as the hemichannels, which, interestingly enough, I think I've heard hemichannel more often than connexon. Is that what they usually say? Do they say connexon or hemichannel? No? Really?
I heard the definition and stuff, but yeah.
Wow, I get to introduce you to something totally new in biochemistry. Woo, good stuff. Okay, hemi meaning part of, right? And so the hemichannels are going to be, or connexons, connects on versus connects in. Okay? Connects on being the half one. The half channel formed from 6 hexagonally arrayed connects in molecules. So again, connects in, that's the transmembrane protein. It'll contain the 4 membrane-spanning helices. You start putting those together and you get a what? Connects on, right? At this point, it's half of a channel, so it can also be called a hemichannel. Okay? And again, those will be your half channels. At this point, you are a hexagon, by the way. So they're 6 hexagonally arrayed connexin molecules. They will adopt a funnel shape. The gap junctions are going to be made of 2 connexons joined end to end in the intracellular space. So each of your cells will have their own connexons, composed of 6 connexins, right? They'll then touch faces, connect together, and that makes your full channel. Is that making sense? And that's what your gap junction is, okay? By the way, this is typically why people call it gap junction instead of cell-to-cell channels. The cell-to-cell channel would involve understanding this stuff right here, right? A little bit more, because literally 2 channels, 1 on each cell that connect together. Okay, so anyways, the gap junctions, again, are going to be 2 connexons joined end to end in the intracellular space. That's why they're called the gap junction. They're a junction crossing the gap. They're going to total 12 molecules of the connexins. 6 and 6, right? Arranged in a hexagonal pattern. Okay. Anybody ever done any work with like plumbing or anything? Or tube? Well, you guys have done tubing. Yeah. Okay. In organic chemistry, you've done tubing, right? I made you connect tubes to vacuum filtration steps. And what is there always whenever you do that? There's always a part where you have an expansions that will fit together, right? To create a tight seal. Okay? And basically, this is the version of that for a cell. It's your gasket, okay? Or your little ribbed glass piece, side funnel, right? Okay, so the gap junctions are going to be formed from the connexins of neighboring cells. And so here we see 2 connexins. This connexin within the plasma membrane of cell 2, connexin with plasma membrane cell 1. This right here would be your extracellular space. It's the space between the membranes, right? Notice that your proteins do extend through to that space. See that? We're literally going to make little tunnels. Okay? Okay, so again, this is a less protein-looking version, more abstract version that allows you to see the overall details easier. Okay, so what's going to happen here is we're going to get 2 different cells. They have cell interiors right there. These then are the membranes. This is your cell exteriors. Okay? They're going to each have their own connexins, which are going to make little tunnels that extend out, right? And then what's going to happen? Anybody have seen a docking on the International Space Station? Or seen 2 boats dock? Yeah. Where they come up side to side and they both have their little rail edge things, and then they kind of clip together something. Yeah, it's like that. Because remember, these are like rafts or boats, right? Your cells are always moving around, always shifting around. they're never perfectly stable, right? And so you hook them together and you get your little tunnel, okay? It looks a lot like the International Space Station one, actually, because they have a vacuum tight in that case. And this is going to be, it's not vacuum tight, but, you know, solution tight. Okay? Okay. If you get a chance, go on YouTube and look at that. And you can, it looks a lot like it. Okay? Anyways, this is your pore. Notice the pore of the two connexons are going to end up extending through to each other. This is why you have an overall pore and channel that you can move stuff through. That's that 20 angstrom pore. Mm-hmm. Sure. Yes. Oh, where does it say intracellular space? Oh. Yeah, that should be extracellular space. Could you send me an email since you caught that? I'll give you some bonus. Yep. Yeah, that's just, when you have that much material, typos happen, right? Thank you for catching that. I very much hate those damn typos. Yes, they will be joined in the extracellular space right here, the two different connexons. Okay, so your gap junctions, these are going to traverse two membranes rather than one. They're going to connect cytoplasm to cytoplasm rather than the extracellular space or the lumen of an organelle. Connexons are going to form a channel, are going to be synthesized by different cells. So remember, one half gets synthesized by one cell, one half gets synthesized by another. Okay? Okay, so aquaporins, these are going to be channels that allow for the rapid and specific movement of water across membranes. They're going to consist of 6 membrane-spanning alpha helices. They're going to contain a central channel that's lined with hydrophilic residues. They're going to transport water molecules in single file at the rate of about 10 to the 6th molecules per second. That's pretty decent speed. That's not that far away from diffusion, right? It's in the same sort of within 1,000 sort of thing. Why do we need these, by the way? Doesn't water cross the cell membranes? It does, but it doesn't do it fast. No. The only reason it does is because of what? Concentration, right? Because the water is like all over the place around you. So the concentration is just massive for the water. But it does it very slow. So positively charged residues towards the center of the channel prevent the transport of protons so as not to disrupt the proton gradients. What would happen if you didn't have any positive charges in there? Are the protons bigger or smaller than the waters? So technically, the protons are actually moving around in water as H3O+, right? Is hydrogen very big? No. So if you didn't have that, those protons are coming with the water, aren't they? Yeah. Yeah. Okay, so the aquaporins, these are going to be channels that are specifically permeable to water. This is actually what this looks like. And so here we can see the extracellular portion. This is the intracellular portion. Notice it does have directionality to it, the protein. It looks different from one side to the other, right? Okay. Okay, so these are the hydrophilic residues right here. They're going to be lined inwards towards the waters. And again, they're going to have some positive charge in there. And they're going to be sized so that the waters can go through them fairly easily, right? Whereas larger molecules will not. Okay, did anybody have any questions about that? Fantastic. Yeah, and please do send me that email, because I really would like to actually have that fixed. I'm going to forget by the time I get to it. I'll be honest with you. Unfortunately. Okay, I actually need to stop that.